So we are today going to move on from circles. Now I reserve the right to go back and do a circle revision lesson in the end of term, as we appear to be dwindling in numbers, while many of you are here and we're going to get through as much new content as possible. But it may be that we have an extra sort of revision lesson towards the end of term. But I want to move on, and today I want to talk about something that sounds very exciting, but actually isn't really as exciting as it sounds. It's called the Factor Theorem. And the Factor Theorem is, like many things in maths, it's making something which we can already do sound a little bit more exciting than it actually is. So that's what we're doing today. Now, if I gave you a quadratic, I am fairly confident that you would be able to factorise that quadratic. And we're a bit rusty maybe, but I'm fairly sure if I sat you on your own, you'd all be able to factorise that successfully. And if this was not just some algebra, but if it was an equation and it was equal to 0, those factors would tell us the solutions, wouldn't they? So the solutions, or the roots, we get from the factors, because what we're doing here is we're multiplying two things together, and we know that if either of them are 0, the answer will be 0. So these are the factors of x squared plus 5x plus 6, in the same way that I can say that 5 and 3 are factors of 15. Yeah, they are factors, aren't they? And quadratics are all very easy, but when we get to cubics, it's a little bit trickier. Now, we have factorised some cubics so far. They were ones without any number term, without any constant term, with just an x, so we could take an x out. But factorising cubics like this, that's a little bit tricky. And now these are both examples of polynomials. The polynomial family is the family made up of algebraic expressions which have lots of different powers of x in. So a quadratic is a polynomial where the highest power of x is x squared. A cubic is the polynomial where the highest power of x is x cubed. And although I don't know how to factorise this one, I know that it would have three factors. And because I've got a single x cubed, I know that each of those factors would have a single x. And I know that the three numbers here would have to multiply together to make -4. So I can already start to sort of build an idea about what those three factors are going to look like. What the factor theorem does is the factor theorem says, I can tell you what goes in these factors if you tell me the roots first. So the factor theorem is doing what I just did here in reverse. It's saying, if you tell me the roots, I'll tell you the factors. And how do we find the roots if we don't know the factors? Well, don't forget what these values are. These values were the values of x that make this equal to 0. So all I need to do is to find three values of x that make that equal to 0. And doing it manually would take a long time, but we've got our calculators. And our calculators have got a table function that allows us to do just that. We did actually do it earlier in the term, but let's have a look. So, if you get your calculator, and you switch it. This isn't going to be usually good for videoing, is it? Come on. And you switch it to table mode, which is number 7 there. And you type in the function. Now don't forget you can use this button here to be x, so you don't actually have to do alpha, you can just use that button there as your x. So type in x cubed plus x squared minus 4x minus 4.
How do I do cubed?
So you just need to, right, so this is the power button, the little hat.
Oh yeah.
So the little hat is, so you do x hat 3, but when you get to x squared has got its own button. So we're typing in that cubic, x squared plus, sorry, x cubed plus x squared minus 4x minus 4. And before I look at the values, I'm going to go to set and just tell it what x values I want to try. You might remember this from GCSE. So I'm saying, right, go on, try x values from -5 to +5. And go up in whole numbers. Don't have to go up in steps of 1. So that was the set button that got me there. And then once I've got that, I just press my exit button and go to table. And table shows me what values you get when you make x equal to those different numbers. And you should find that when I make x equal to -2, I get 0. That means that this cubic equals 0 when x is -2. We have a way of writing that. We say, okay, f of -2 equals 0. That means that x equals -2 is a solution and x plus 2 is a factor. So because f of -2 was 0, I could say that means -2 is a solution, x plus 2 is a bracket. Was that the only solution, or we should be able to scroll down the list? Come on, sorry, I don't know why this is suddenly gone dodgy on me.
-2, -1 and 2.
There we go, yeah. -1 and 2 are also, so f of -1 is 0, so that gives me the solution x is -1, which gives me the factor x plus 1, and then f of 2 is also 0, so that gives me the solution x is 2 and the factor x minus 2. So all we've done there is this process in reverse. Okay, we've said, right, in this case I know the factors so I can work out the roots. Here we're working out the roots by a different method, and from that we are getting the factors. And I'm not going to do the full multiplication thing. I could multiply those two out and then multiply by that, but 2 times 1 times -2 does give me -4. Bingo. I've factorised my cubic using the factor theorem. I'm going to state the factor theorem for you. So the factor theorem says for any polynomial, and we use polynomial f of x, for any polynomial f of x, if f of some value equals 0, then x minus that value is a factor. That's the factor theorem. And we're today going to solve 3 sorts of problems using that theory.
How would they expect us to do this without calculating?
Well, you'll see how they actually ask it in exam questions. So you wouldn't actually get an exam question that asked you to do that. But you can always use this method to check. So the first sort of problem I'm calling fully factorised. Here's a cubic, fully factorise it. All right. Can I get you to use a similar approach and factorise 2x cubed plus x squared minus 18x minus 9. See if you can use a similar approach to factorise 2x cubed plus x squared minus 8x minus 9. So Will has, just giving him credit, Will has correctly spotted that with this one there are only 2 values that make it equal to 0. Well, we say that, I mean we've only tried from -5 to +5. We could have tried more values, but we've so far only found 2 values. Was it 3 and -3 and 3? So our factors would be x plus 3 and x minus 3. Now, I could widen the search, and I could say it may be that it's not going to be whole numbers, so I'll try some decimal numbers, but I wonder if we've got enough information now. How many x's do I know will have to go in that bracket?
2.
It's got to be 2, hasn't it? To give me 2x cubed, sorry? Yeah. When I multiply that out, and I perhaps should have started, it would have made it a good start, wouldn't it, to have got you to do one of those triple bracket expansions where you do the first two and then you take that answer and multiply it by the third. Yeah, but if I did that, that would give me 2x cubes. And the other thing is I need to end up with minus 9. And I've already got
How
one.
do you know that it's not any of the other two that's 2x?
Well, that's a really good question. That's a really good question. Can I, if we just finish this, then I'll address that. So that's got to be a plus 1, hasn't it? Because that would give me, and that means that 2x is minus 1, so x is minus a half. Now, you asked a very sensible question. If one of the others was 2x, I would have had to have made this, for example, for I know that minus 3 is a solution, so if that's 2x, it would be 2x plus 6. And if that was 2x plus 6, this would become x plus a half. So you're right, I could have written the factors differently. The solutions would always be the same. But yes, there's more than one way of writing that factorisation. So we have fully factorised a couple of cubics using the table function. But Harry asked a very sensible question. Yeah, what about people who don't have these fancy calculators? I mean, actually, all calculators have a table function, but this is still one of the things where we are still expected to work a little bit manually. So let me show you how this would look in an exam question. Okay. So what we've got to do really is we've got to sort of forget the table function for the moment. All right, the table function is a way of fully factorising, but here's how they ask it in exams. So it says show that x minus 1 is a factor of x cubed plus 6x squared plus 5x minus 12, and then go on and factorise the rest. And it's not enough just to say, okay, I'll go into table function, I'll make x equal to 1, that's enough. That's not enough. I have to do that manually. So the factor theorem says that if a is a solution, x minus a is a factor. So if I can show this is a factor by checking what f of 1 equals. Okay? So if x minus 1 is a factor, x equals 1 would be a root. So let's check to see if 1 is a value that makes this equal to 0. So I'm going to work it out, and I'm going to set this out so I'm showing my method. So I'm going to make x equal to 1. So I'm going to do 1 cubed plus 6 lots of 1 squared plus 5 lots of 1 minus 12. And, you know, I might even put the 1 cubed in. So, you know, I'm really showing my working in a sort of exaggerated fashion. And 1 cubed is 1, 6 lots of 1 squared is 6, 5 lots of 1 is 5, take away 12, yeah, that's 0. So, x minus 1 is a factor. So that's me sort of pretending I haven't got the table function. That's me just saying, okay, I can prove this is a factor by proving that x equals 1 makes that polynomial equal to 0. Okay, so here's where we've got to then. We've got this polynomial, and I know that x minus 1 is a factor. But I'm no closer to the other two. We are close to the other two because we could use the table function, but okay, we're not going to. So here's what we do, and it's a really neat technique. I really like this technique. What we do is we say, okay, I don't know what those two other factors are, but if I was to multiply them out, they'd give me a quadratic, wouldn't they? Those two other factors would give me a quadratic. And quadratics look like this. They always have some x squareds, some b's, and a number. That's what they look like. I then say, okay, can I work out some of these values to start with? So, what about the value of a? Well, that's nice and easy, isn't it? I've got a single x cubed here, so I know that's going to be a single x squared. So actually, a is 1. There is no coefficient in front of the x squared. What about c? Lily, what do you reckon about c? We look at what we've got here. What do you reckon c's got to be? It's something to do with minus 12. In fact, I would go so far as to say it is minus 12. Yeah. But we don't know what b is. We don't know what b is. So here's what I'm going to do. I'm going to get you to, now you may find at the end of the day, when you're used to this technique, you don't need to do this next bit in full. You can sort of take a shortcut. But can I get you to multiply out that right-hand side, sorry. There'll be b's in your answer. Can I get you to multiply that out for me and write out what that gives you? Okay, so I'm multiplying out that right-hand side as it stands at the moment. Thank you, Charlie, for pointing out that it should have been a plus 12. Okay, so we've got this. It doesn't look very pretty, does it? You know, I mean, I can't, normally I would peanut, and I can't peanut because I can't put those two things together. But here's the neat trick. So we're saying that this cubic, the cubic we started with, is equal to this. That's what that sign means. It means this side has got to be the same as that side, and that means I've got to have the same number of x cubes, the same number of x squares, the same number of x's, and the same number on both sides. Well, so far that's all looking good. I've got 1x cubed on both sides. I've got a minus 12 on both sides. But with the x squareds and the x's, I don't know, because I've got b's in there. So what we do is a process called equating. Equating says, I know that I've got to have the same number of each term on each side. So let's look at the x squareds. So I'm going to equate the x squareds. On the left-hand side, I've got 6 x squared. On the right-hand side, I've got minus 1 x squared, and I've got b x squared. So can you see what I've done there when I equate? I haven't written 6x squared, I've just written 6. So on this side, that's the number of x squareds on the left, and this is the number of x squareds on the right. So I now know what b is. I now know that b is 7. Now, some of you will now see how you maybe didn't have to do the whole multiplying out, because actually, in order to equate the x squareds, I only need to work out those two terms. But I think doing the whole process it's good practice at this point. Right, so what does that mean we now know? So I now know that this is a 7. Plus 7? Yes. I can factorise that. I've done what I've asked. Okay? Now that's a whole lot more hassle than using the table function on your calculator. I will absolutely accept that. We would have got that answer instantly with the table function, just like that. And of course you can check that. We're just in one of those positions where this is something that we're expected to be able to demonstrate manually. And I think it's a neat trick. It's called equating. If you look in the textbook, and I'm talking to Beth and Grace specifically, they use a different technique that we're going to do tomorrow for this other than equating. I do equating first because I think it's easier. But anyway, so fully factorise, just have a go at 3 and 4. So this is on page 145, I believe, 145. 3 and 4. So it's just 2 more of those, and then that leaves 5 for independent study. So I substituted -1 in, and I was really clear, it was a real exaggerated substitution, really exaggerated in my method. -1 makes this equal to 0, so -1 is a root. Don't forget, if this was a graph, that would be a place where it crosses the x-axis. So that means that x plus 1 is a factor. That's the reverse to the way we've always done it so far. So I know that this is true, I know that this is true. Again, single x squared, so I know I have got an a, and c has got to be -35. So I'm going to multiply that out, and then I'm going to equate, and just for the heck of it, this time I'm going to equate my x's, but it doesn't matter, x's or x squareds. 3 and 4. Question 7, part A, is the next one where I'll show you that in a minute. So this time I'm going to equate the x's. I've got -33 x's in my original polynomial, my original cubic, and on this side I've got b -35 x's. So if I add 35 to both sides, b is 2. I can then trickle that back through my solution and scratch my head a bit, and yeah, I can factorise. And that's the end. They only wanted us to get that far. Factorise it completely. That's what we've done. X plus 1, x plus 7, x minus 5. Now, if you are working on 4, leave a little bit of space. I know I'm rushing you on, but I'm hoping you can fill in the gaps. Could we have a quick look at 7? Is there any? Are we okay with that?
Yeah.
Please ask. Okay. I just wanted to have a look at 7. Can you spot with number 7 what is missing? I know it's a slightly different question. They're asking you to sketch a curve, but what don't they give us to start with? They don't give you one of the factors. That's right. What you're expected to do, and what we used to have to do, so this does answer your question, is you're expected to try different values until you find one that makes it equal to 0. So in the old days, you'd say, right, it's probably going to be 1 or -1 or 2 or -2. So in this question, I am going to use the table function to get one value, one factor. So for this one here, 2x cubed plus 5x squared minus, I am going to use the table function to find one factor, and then I'm going to go through the same process that we've just been through. So I'm playing dumb, all right? And I know it's a silly thing to have to do, but there we go, go figure it. So I'm going to use the table function to find one factor.
How can I just find all of them?
And at the same time, I'll probably find all of them. I'm then going to quickly do the equating method. And I'm going to show my working. So I'm to find this one, I'm going to say, let's say it's 1, I'm going to find f of 1 equals 0, therefore x minus 1 is a factor. So go on, quickly use your table function, see if you can find a factor. It's almost certainly going to be 1 or -1 or 2 or -2. It's unlikely to be a mile away from that. So we had a number of options for where we started, because the table function is going to tell us, a couple of factors. We could have done f of -3. I chose f of 1 because it was just easier to do this bit. So rather than just getting the table function to do it, having got the table function to tell me the value, I showed some method. I then worked out that a had to be 2 and b had to be 3. I multiplied out, so I'm at my equating stage now, and I think it's really important to annotate and say what you're equating. So I'm going to equate x squareds again. Doesn't matter whether you do x squareds or x's. So I've got 5 on this side and -2 plus b on that side. 5x squareds here, -2x squared and a bx squared. And those two have got to be the same. So b is equal to 7. Going to work? Does that work?
Yeah.
It does. All good. Good. So if b is 7, oh, it's because you've got the 2x. It's always harder to factorise when you've got 2, but because Harry kindly told us that -3 was a solution, I know x plus 3 is one of the brackets. So this will have to be 2x plus 1. And that does work, doesn't it? It doesn't look like it will, but because you've got the 2x, you get, if you multiply that out, it would give you that. And because you all hopefully saw the table function, you all saw that x minus 3 was a solution. Sorry, x equals -3 was a solution, so you all knew that x plus 3 was going to be there. So that does help with that final step. Now, of course, this question is a sketching question, and Pat's absolutely right. We've done this sort of thing before. You know, we now know that x is 1, x is -3, and 2x would have to be -1, so x is -1/2 are our roots. And that means that's where this cubic would cross the x-axis. So it crosses the x-axis at -1, -1/2, and, no, hang on. It crosses the x-axis at 1, -3, and -1/2. I also know that when it crosses the y-axis, I just ask what do I get when x is 0? -3. And I know it's a happy cubic. So something like that. Remember, we don't know where the turning points are yet, but that gives us a way of sketching. So I've put on independent study question 5, although some of you didn't go to question 4, we're in the middle of question 4, I rudely interrupted you, so I think a couple of those is plenty. And then you might choose to do one more of those. I think certainly hammering that technique, that manual version of what the calculator makes so easy, is really worth doing. And then next lesson we can look at the other 2 sorts of questions that we might be asked.